Yes, my name is Gabor Stepan, and I have the honor to chair the next keynote speech given by Harry Dankowicz. Harry, your microphone.
Thank you.
Harry Dankowicz was graduated from KTH in Sweden with a master degree, and then from an even higher institute, higher reputation institute, Cornell University, with a PhD. At the moment, he's a professor of mechanical science and engineering at the University of Illinois at Urbana-Champaign, after a short time that he spent at Virginia. From several awards and activities, I would mention only two. One is that for 10 years, he was the editor-in-chief of applied mechanics reviews of ESME. During this time, the reputation of this journal went up to a very high level. And the second one is, at the moment, he's a program director at the National Science of Foundation, at the most important program for us in dynamics and control. So this is well, the title cannot be seen clearly, but maybe you will explain us the title. So Harry, the stage is yours.
Thank you very much. Now, okay. And you're fixing the slides, excellent. Well, it's a delight to be here. I'll just say a few words about how excited I am to be back in Rome after actually 4 years since I was here last. I'm happy to see lots of old friends, and I'm hoping to make some new friends, and I'm hoping the microphone will work, and that, Gabor asked me if I had a power pack with me in case the power went out. I didn't bring one, and they're still working on the slide, so hopefully, yes? Yes, but I mean, I have stuff on the slide. So, all right, so the first word is design of self-excited oscillator networks as nonlinear dynamic sensors, and this is what's going to happen on every slide, so hopefully they'll fix it. And I think we must have lost, no? It's just a PDF. Yeah? All right, so I have a few takeaways, and I'll see if I can try to remember what they are. So the main first takeaway of this is that the work is going to involve coupled oscillators in some sort of network topology, and that the topology matters. The way that different oscillators are connected to each other can be leveraged and utilized for purposes of sensor design. Secondly, I'll present to you, this is a very truncated talk, as you can see on the slides. I'll present to you an idea for how to design a network of sensors that responds to an external excitation and continues to be responding even after the excitation goes away for some time until it eventually returns to a quiescent state, and then takes some time before it can again respond to excitation. So that would have been my second takeaway. And then the third takeaway, I don't remember what my talk is about. The third takeaway is a type of sensor design, 1 minute they tell me, is a type of sensor design that uses an in silico oscillator coupled to a physical oscillator for purposes of high mass gain sensing. This is an awesome talk, yes. Excellent. Well, that's the last bullet there. All right, so I have a thought experiment. I want you to spend a lot of time thinking. Excellent. Thank you very much. I'm now leaving the thing. Okay, yeah, so I want you to think about a social network, as we are all familiar with and probably part of these days, that couples individual agents, suggested on the right, a network that allows for sharing of information, some type of distributed processing of information, and allowing agents within the network to respond to signals in the environment. Now these signals, so the information that may be impinging upon the network, could be picked up from the environment, or it could actually be generated purposely within the network. As we know, there may be agents within the network that introduce information into the system in order to affect its behavior. And that information is then, of course, communicated through the network, as we are all well aware. Now, the configuration of the network itself may act to amplify some of this information or suppress the information, and also, of course, distort the information. And by information here, I don't mean the news about the world, but I mean signals, right? The type of vibration signals and things that we are interested in. And I'm speaking here in terms that hopefully you relate to, having to do, for example, with the attention level of an individual agent to the signals that are coming in, the way it's interested in certain signals in the sense of being resonant with certain signals. And then finally, as we know, our attention then can wax and wane as information is received, transmitted through the network, and as agents act in response to the information. So this is the setup. The top of the slide says it's a distributed game of telephone. I'm not sure if you're familiar with the game of telephone, but it's when I whisper into Walter's ear and he whispers into Mohammed's ear, and then as it goes down the line here, whatever I said is completely lost, and whatever sort of remains is a function of what happened in the network. So I'd like you to think of a way to design a network like this in a purposeful way so that when there is no external signal, the network remains in a quiescent state. Then if there's a brief external signal that excites the network, and that excitation may be very local, by the way, maybe only one of you receives the signal, that signal is then transmitted through the network, and the network begins to exhibit a sustained response even as the signal of excitation goes away. Now, after some characteristic time, minutes, hours, or days, the network should return to a quiescent state, the one it had before the signal came in. And it shouldn't be sensitive to another signal for some time. So it should need some time to sort of rebuild itself to be able to again respond to an external signal. I'd like to design a network to do this, and I'm proposing a very simple mechanical model, in this case consisting of 4 coupled oscillators, 4 masses that can oscillate vertically. Dampers here are suggested as possibly being nonlinear, and if you look on the equation on the left, which should be familiar to you all, the damping matrix in the first diagonal term has a nonlinear component, which is effectively a van der Poel's type of damping term. All right, so my goal is going to be to take this network with 4 oscillators that are linearly coupled, weakly nonlinear, and I'm going to design rate laws. My goal is to change the damping on the fly in the system, specifically the linear damping. So the nonlinear damping I'm not going to touch, and my goal is to change the linear damping on the fly so that the system as a whole exhibits a hysteretic response, right? It sits quietly, gets excited, jumps up to something, remains there for some time, eventually drops back down to what it did before, remains there for some time before it's able to start again. So multiple scales was mentioned, and since this is a conference in honor of Ali Nafis, among others, if you apply multiple scales method analysis to this network of 4 oscillators, under the assumption of weak damping, you end up with the slow flow dynamics, in the slow time scale, that show how the phase and amplitude of a particular unstable mode varies with time, with slow time. And of course, I can look for equilibria in the slow time dynamics, which would be the type of linear type modes that we have looked at, although in a nonlinear system. And so in the graph on the right, the blue curve represents the equilibrium at 0 and the family of periodic solutions obtained as shown on the left. Right? So these are all solutions for where the slow flow equations have an equilibrium. So we recognize that a solid curve is a stable equilibrium at the bottom. The equilibrium becomes unstable as we cross here at 1. There is a branch of limit cycles that is an unstable branch of periodic orbits here, and then stable limit cycles at the top. So if the damping is constant, the dynamics is described by the gray arrows. If I start with an amplitude, let's say here, at this damping value, I'm going to drop down to the equilibrium. If I start above the dashed line, I'm going to go up to the solid curve of limit cycles. But the red curve is suggesting the possibility of hysteretic behavior, right? Where I start with a damping value perhaps slightly below the Hopf bifurcation. This is a Hopf bifurcation here. I jump up over some period of time. These are slow dynamics to the limit cycle. And then if I vary the damping and increase the damping all the way past the saddle node bifurcation, I will follow the branch of limit cycles until I drop down again to the equilibrium. And then it'll take me some time before I reset the damping and can again respond, right? So this is the hysteretic behavior, and this is what I want my network to do. And this is what the dynamics might look like as I vary the damping. The orange curve is the damping, the blue curve is the response to the system. And so you see that when the damping is sufficiently small, the dynamics grows and eventually becomes this large-scale limit cycle. And then if I start increasing the damping, the amplitude shrinks until eventually I drop back down again. So it's the same behavior as I showed in the previous slide. Now, the picture on the left is what I just shared with you, but I want to change the damping in real time. I want to design my system to have a damping component, damping variable, that has a time history. So at the bottom of the slide, for those in the back, it might be difficult to see, there's a differential equation for the damping. And if I introduce that differential equation and design it properly, instead of the picture on the left, I get the picture on the right. Here on the right, you can see that the damping and the amplitude are varying along the red curve in time. Okay? This is slow time, very slow time, but it's built in through this differential equation. So I have my original dynamical system with these oscillators, and I've added a differential equation that governs the behavior of damping over time. I can do this in the case of strong damping as well. So if the damping coefficients are very large, a similar multiple scales analysis applies. I again get an amplitude equation, just like we're all familiar with. I get a curve of limit cycles or periodic orbits, some of which are unstable, some of which are stable. And I can again design a damping differential equation, sort of an internal state variable. I can treat the damping variable as an internal state variable with its own governing equation that will produce the type of hysteretic response that I just showed you. So here's an example of what that looks like. This is a node network now with 15 nodes. And you're seeing the oscillations. This is the envelope of oscillations, right? This is the amplitude of oscillation varying with time. You get the initial jump up. You get the slow, steady persistence in the high amplitude state. Eventually it drops down, and it takes some time, as is suggested over here. It takes some time before I come back all the way to here and can again react to an impulse. Okay? Things get interesting if you like to have fun with bifurcation analysis and different ranges of parameter values. You can do catenation analysis. You can apply some asymptotic techniques to this work, and you end up with maybe even three-dimensional pictures that represent the surface of periodic orbits. The equilibria are down here. This is where the equilibria are. Let's see. This is where the equilibria. I'm trying to remember. Well, I cross here, and I get the Hopf bifurcation. So I have a Hopf bifurcation in red, and so I have stable equilibrium below, and outside, an unstable equilibrium inside. And in the region where I have an unstable equilibrium, I can jump up to this surface of limit cycles. In some other cases, again, this is the 15-node network. There are many modes that are potentially unstable or interacting in a similar region. So I'm just showing you beautiful pictures, not expecting you to remember or memorize any of it, just to suggest that it's a lot of fun stuff that can be done by looking at the way that these instabilities occur with a network with some topology. And the important thing here is that the topology is part of the analysis. So in general, it's possible, this will be in a slide with equations, for an arbitrary topology, in other words, an arbitrary way in which the network is connected, I can derive a modal matrix. We know how to do this for linear systems because the topology is basically given by the stiffness matrix in the linear case. And so I can diagonalize the stiffness matrix using this modal matrix. So this is just linear analysis. Now, if I assume that one of my parameters here is, or the parameters are small, and I have a single nonlinear oscillator, so I have a network with linear oscillators except for one nonlinear oscillator, then there is an instability that occurs, just like the Hopf bifurcation I showed you on the previous slide, although this is for a general network. I can do a modal approximation. This modal approximation now is in terms of the linear mode shape with some slowly varying amplitude and phase, and I can derive an amplitude differential equation which depends on the topology. Everywhere P shows up, that's where the topology enters. And I get limit cycles, or periodic orbits, where this equation has equilibria. So that's an equation for those limit cycles. And now the goal, as I said, is to design differential equations, design rate laws for the damping coefficients. And so I can do this. Here I'm suggesting a formula, again, in terms of the topology. One thing you may note, if you've paid some attention to what's going on, is that the rate law depends on this quantity A, And the question is, what does A represent? So on the previous slides, A was the slow amplitude. But I don't have access to the slow amplitude in a physical experiment. That's just a theoretical construct. In a physical experiment, I can take the actual signal and perform some type of Fourier analysis using, in this case, also the connectivity of the network to compute a force. And I can calculate that force and put it in here. So this is looking at the interaction force between different elements. In order to compute a rate law for the kth damping that depends only on the force experienced by the kth node. So this becomes a distributed feedback loop or a distributed rate law that allows this network to perform this type of hysteretic behavior. All right, that was the first piece of my talk, talking about how to design hysteretic behavior in a network with a nonlinear node. The next game is that of Mad Libs. Mad Libs is when I write a sentence and then I give the paper to you and you write another sentence, right, below it, and then we unfold all of the sentences eventually and see what we wrote, right? So this is where you only hear something and have to build on it. This is a kid's game. So the inspiration is the following. Suppose that I have a network in which a particular agent can transmit information to the network, but cannot receive information from the network. It thinks it's receiving information from the network, but instead it turns out that that information is received from a computer that generates the information based on instructions that someone is giving it. So I'm part of a social network, I think, but it turns out I'm not actually getting any information from the network. Instead, I'm getting controlled information from the matrix, so to speak, if you recall the movie. All right, so the question now is, what should the experimentalist do in such a case in order for me and the system to behave as if I was receiving information from the network? Okay, so I have a network in which I am a member. I'm interacting potentially with other members of that network. I can give them information. In theory, they could give me information. We might do something together, but that is interrupted by this computer and this experimentalist. And now the goal of the computer and the experimentalist is to give me information so that I behave the way I would have behaved if I was talking to my neighbors. You're sort of following that? Okay. So what instructions should I give, or should this experimentalist give to the computer? And can we determine what those instructions are iteratively? So I'll give you an example of what this means in a second, but it's a general thought experiment that I hope I'll be able to engage with you after my talk and later this week. Okay, so back to coupled mechanical oscillators. I have a linear oscillator on the right. I have a nonlinear oscillator on the left, again with some type of van der Pol damping term, as you can see in the top row of the two equations here. And the key observation here is that the oscillator on the right has an additional mass attached to it, as you would if you had a sensor that was trying to detect a virus, let's say, attaching itself to a cantilever. The two stiffness parameters are the same. There's a coupling stiffness that couples the two oscillators with each other, but beyond that, it's a relatively simple mechanical system. And the question, of course, is, can I somehow operate this system so that it detects that additional mass, right? That would be the goal. I'd like to be able to measure something about the system so that the additional mass is predictable from that measurement. Now, it turns out that you can do some other types of perturbation analysis to deduce the following fact. If the nonlinearity is weak, so mu is a small number, if the damping is small, if the coupling is small, and if delta m is small, then you can do perturbation analysis to relate the ratio of the two amplitudes of oscillation. So I have U2 oscillating and I have U1 oscillating. Take the ratio, call it alpha, and then have delta be the ratio of delta m to m, so the mass ratio. So given the mass ratio delta, there is an alpha which describes the relative oscillation of the two masses. Here, kappa and gamma are given in terms of the coupling stiffness and the damping term. And so there is this relationship. This relationship suggests that if I can measure alpha, then I might be able to compute delta, clearly, just using this formula. So delta is not observable, alpha is. I might be able to predict what the mass is that has attached itself to that second oscillator. Okay, so this is a nice system where I have a predictable formula. Now the question is, how do I build this system? How do you build a Van der Pol oscillator? I mean, certainly in the good old days when Van der Pol did this, he had some sort of interesting electronic circuit that accomplished this, and I know colleagues in the audience who have worked on building similar things to realize these types of nonlinear damping terms. But my goal is going to be the following. Instead of building an actual physical network that couples these two oscillators, I'll put one of those oscillators in a computer and simulate it, and the other oscillator will be a physical thing. So I'll have a software-in-the-loop realization in order to quantify this mass that has attached itself. Okay? So in terms of the game that I showed you before, I have these two oscillators, but one of them, this one, is receiving information from a computer. And the question is, how do I design the information that it's receiving from the computer in order for the full system to behave as predicted by this formula? This formula shows itself in the following way. You can see that the amplitude ratio depends on the mass ratio according to this graph. The solid curve and the dashed curve is the result of exact numerical analysis versus the perturbation method. And so one thing you notice is that for very small mass ratios, I get a significant amplitude ratio with a good slope here, and the slope is the gain of my sensor, right? So good size slope is a good gain. And on the right, if I vary the coupling stiffness, I get different amounts of slope. And so I have a tunable system. If I can vary the coupling stiffness, I can tune the sensitivity of this sensor. Okay, now I told you in that game before that I'm in this social network, and I think I'm talking to my, my buddies, but instead there's been a cut. Something has been interrupted, and so instead of me being connected to my buddy, I'm now connected to an actuator, and the actuator pretends to be my buddy. The question is, how should the actuator do that in order for me to believe that I'm still talking to my buddy, and so that the system as a whole behaves as if the actuator wasn't there and it's just a coupled system? Okay, let me say this again, right? I'm looking to have this picture be the same as if the two systems were connected. But all I'm allowing myself to do is to feed an actuator signal into the second system. How do I drive, or how do I determine that actuator signal? Well, I could drive it with some signal sigma 2. I could observe the response of this system. Maybe what sigma 2 does is it pulls on the mass. The mass oscillates as a result of the additional mass added and the input signal, and eventually it reaches steady state. That steady state is the signal U2SS that's shown at the bottom. All right? I can measure that signal, and I can put it into my computer and do something with it in order to get out a new signal, U1SS, which let's say could be the steady state behavior of this system. And now I have both U1SS and U2SS, and I know that sigma 2 should behave as if this was coupled to that with that spring. You remember the spring that connected the two? So my goal is going to be that that U1SS minus U2SS times that coupling stiffness should equal sigma 2. But it won't. It won't, because I put the wrong sigma 2 in, and I got the wrong U2 out, and I got the wrong U1 out. So it won't. But now that I know that it doesn't, I can adjust my guess. I can change my sigma 2 and see if it gets better. Well, it won't. It'll get better, but it won't fix it. But then I can keep adjusting it iteratively until it actually does give me precisely what I was looking for. That's the iterative method that I was suggesting before. In other words, I think I'm talking to my buddy. I'm giving my buddy information. My buddy's not able to talk to me. Instead, a computer talks to me. But the computer figures out how to give me information so that I think that I'm part of this loop, right? So that the mass on the right thinks it's part of the loop, and the behavior of the system is exactly what I wanted it to be in order to measure that additional mass. So here is an example of what those iterations look like. Let me start with, by the way, there was an actuator on the previous slide, as you noticed, those of you who paid a lot of attention, noticed that there's actually a sigma tilde that's being fed into an actuator, and then the actuator is pushing on the system on the right. I can't really give it a sigma 2. I can give it a sigma tilde. So my goal is to figure out what sigma tilde should be in order for all of this to come together. And I do that through iterative methods. So I start out with sigma tilde being 0. I give it nothing. If you give the system on the right nothing, what does it do? Nothing. It just sits there. So that's my U2SS. I take that U2SS and I use it to calculate a U1SS, which turns out to be something, but it's not the right thing in order for the system to appear coupled. And so then the system iterates. It comes up with a new sigma tilde. In the first iteration, the new sigma tilde is the curve with circles. And as you can see over here, this is what's going on with the coupling term. It says KC U1 minus U2. This is the coupling term. So in the first step, the coupling term is the blue dashed curve. In the second step is the curve with circles. And then after a couple of iterations, only a few of them, I have apparently converged to a solution for sigma tilde and a solution then also for the coupling term that is exactly what it needs to be in order for the uncoupled system to behave as if it were coupled. And this graph is showing that I can vary the damping in the linear system, in the cantilever. I don't know what the damping is, right? We don't have the damping explicitly. We can calibrate the system by doing a bunch of experiments. And this is showing that even for a wide range of damping values, on the left, if the actuator is just a delay, on the right, if the actuator is a PD-controlled servo system, for a wide range of damping values, for a wide range of values of the mass ratio, every circle here means that the iterations converged. The solid curves are predictions, the circles are iterations converged. The method works. All right, so I am coming to the end. I've presented to you two different ideas for how to look at a network of oscillators. I've tried to, in the short period of time I had, to give you some inspiration from the context of social network analysis and things that we know more about than we wish to know these days. The first example I showed you involves self-excited dynamics and hysteresis, which we're familiar with. It occurs in a network that has both linear and nonlinear oscillators when the linear damping is not large enough to stabilize the system. When you have a single nonlinear oscillator, a van der Pol oscillator, it's always unstable. The equilibrium is always unstable. But if you couple to things that are linear, the linear damping can stabilize the equilibrium if it's large enough. So if it's not large enough, then you get this balance between the linear and nonlinear damping, and you get this possibility of a hysteresis loop. And what I showed you is that I could design a rate law so that internally the system, through a distributed calculation, goes through a loop in response to an external excitation. What this internal dynamics do, the dynamics of the damping coefficients, is it adds memory into the system. It allows me to remember my previous state. That's what hysteresis is, right? Some sort of memory. So I'm adding memory. I can do this over separable timescales. I can decide what the timescale should be over which I retain the memory. And as a result, I'm able to both sense things and act. The other thing I showed you was a very simple example where I can use software in the loop of a physical device in order to implement a very simple network topology of just two mechanical nodes that realizes a kind of sensor design. But I hope you can imagine that with a software in the loop realization, you can do anything you want in the software. Your network could be very complicated. The way it's connected to the physical system can be arbitrary, and you have a great opportunity to tune your sensor to behave in interesting ways. And the key idea here is none of this is real time. There is no real-time coupling between the oscillator on the right and the oscillator on the left. It's only through iterations that I determine the right input to produce the coupled behavior. So no real-time stuff, which I know a lot of other people have worked on. And so iterations, in addition to allowing me to find this ideal behavior, it also eliminates the effects of the actuator. that actuator I showed you, I mentioned in one case was a delay term, in another case it was some sort of PD servo. But in principle, I don't know what the actuator is doing, right? The actuator could do all kinds of interesting things that I'm unable to quantify. However, with this iterative method, I can entirely eliminate the impact of the actuator. So if that's not clear to you, I'm happy to show you more about it later on. And this is, of course, as long as the system is behaving periodically in the steady state. So now for a few questions. I did introduce all of this in the context of social networks. I worked for a while on honeybees and colonies of honeybees. I've also done some work on small groups of humans, not really large social networks, but small groups of human participants. It's interesting to ask the question, I mentioned it in the context of the game of telephone, right? I whispered to Muhammad and so on. And it's interesting to ask what happens if there is Ahmed in here introduces on purpose a new term into the chain that I didn't even say. You just like to do it, right? It's your thing. You're the self-excited oscillator. You introduce energy into the system, whereas the rest of us are just dissipating energy. How does this behave? What is going to be the response of the system as a result? And we know that biological systems like honeybee colonies may be very well designed to respond to external stimulation, and they may want to remain excited even after the external excitation goes away, because they need to be able to gear up for winter, let's say, and they have a little bit of a hint that winter is coming, so they start preparing themselves for that. Or if it's danger, you want to be alert for a while after danger is gone. But then you want to come back and settle again. And then usually what happens with biological systems is it takes them a while before they're able to respond again. That's the refractory period. So you have that hysteretic loop. And so I'm, of course, asking, do these hysteretic effects occur in human and social behavioral communities? And I'm interested in your thoughts on that. Autoacoustic emissions is this thing where your inner ear, some of you may have worked on this, where your inner ear generates sound. It just starts generating sound. It's a self-excited oscillation within the ear apparatus. And so I'm wondering to what extent these kinds of ideas apply there. I mentioned here that I could do all kinds of creative things with my network. And so, of course, one might ask then, what is the optimal design of such a network that will give you high mass sensing sensitivity? And then this is something I'm really curious about. Can we, this kind of iterative thing where we don't have to do real-time coupling, can we do that with embedded implants? Can we have an embedded implant that figures out through iterations with us, not reinforcement learning, but maybe, this type of stuff, figures out how to interact with us in a way that makes us behave in a more natural way. So with that, this was work largely done by my PhD student, now long ago graduate, Yu Mao. Work that has appeared in Nonlinear Dynamics and ASME journal. And if you want to know more about that, you can also look at Yu's dissertation. Some of the graphs that I showed you, especially the two-dimensional surfaces and so on, were obtained using the software package coco, which I'm happy to tell you more about. And I should acknowledge support from the National Science Foundation, both for the work through a grant, and also, as was mentioned, since I serve as a program director with the National Science Foundation, some of this work was done during that time. And as you note here, I take full responsibility for everything I said, and none of it reflects NSF. And this is how you reach me, and thank you for your time.
Thank you very much, Harry. Would you stay here still for a couple of questions? So we have some time for some. Please, okay, I will try to get there with my microphone.
Thank you very much, Harry. That was very interesting. And this implementation of a software and coupling it with a system, I think it has so many practical applications. As you said, it opens much beyond even the application you cited. Yeah. I have a simple question in terms of a sensor point of view. So what motivates you to go after mass detection using this technique? Do you have evidences that would be advantageous compared to mode localization or bifurcation-based sensing and so on?
Oh, I see.
Thank you.
Thank you for that question. I appreciate it. I will tell you that one of the things that motivated me was your neighbor sitting right in front of you there. Hiroshi's work on mass sensing and using self-excited oscillations, and it was sort of taken from that perspective. So I don't think I have an answer to why this would be better than anything else. What this, of course, did was it avoided that real-time coupling thing that I think most other implementations have used. And so on the mass sensing side, as you point out, there are other techniques for mass sensing that look at amplitude ratios and localization, and it's all a question of gain, right? It's all a question of how sensitive is this to the mass that's being detected. My hope, as I was suggesting to you before, is that by putting much of it in software, and I think Hiroshi's work and others have already hinted at this, by putting much of it in software, you can generalize and create topologies that you couldn't imagine that then allow you to tune and get much better sensitivity. That's the hope. So.
Okay, thank you. Just a quick second question.
Excellent presentation, Harry. Very nice idea. So I was wondering if the sensitivity is in any way related to the size of the network, or it doesn't matter.
Great question. So, let's work on it afterwards. I don't know the answer to that. But
Thank you.
Great question. I mean, there's a lot of open things here. This is recent, so I'm hopeful that you'll find it inspiring.
Okay, we had a third question here. Maybe this is the last one.
Yeah. Thank you. Fascinating talk. Very brief question about the second problem.
Yeah.
It kind of smells of the Turing test, which is, right? There's like a spoofing thing.
I was hoping you'd think of that.
Spoofing thing going on here. So my question is, why not use real-time sensing to improve the software, like one-way sensing? Is there I mean, looks to me like it could only make it better.
Help me out. I mean, there's still real time.
Like the software you said the software kind of gets disconnected from the real system.
That's correct, yeah.
I'm saying, why not enable it to, sample the real thing at least once in a while and implement that to improve the accuracy or whatever you're looking at?
I mean, certainly it's conceivable that some combination of this kind of iterative technology and real time would be ideal. The issue with real time for me is not so much the sampling of it's not the sampling of the physical system that I'm concerned about, it's the driving of the physical system by the software. And if that has to happen in real time, then you have all the consequences of time delays and computational delays and actuator delays. So with that, I'm being pulled off the stage here, so yeah. Okay.
I was very happy about this with the time delay. Thank you very much. Let's go on.